Good morning, all. Let's tackle exponential functions, the next level today. We're going to apply what we've been talking about all year about the parent functions and the shifts up, down, left, right, and the stretches and compressions. We're going to apply that today to our exponential functions that we were talking about yesterday. So here we go. The h is hidden up here in the exponent this time. So here's our x minus h that you're very used to hearing, and the k is the one that's off here by itself as it has been all the time, and the stretch or compression comes from the part that's multiplied times the initial parent function. Reflections, if you remember, reflections are if this number happens to be negative. So all of the same properties that we've been talking about all year apply here as well. It's just that exponentials, there are a variety of different parents to consider, because if you remember, this number right here gives us our basic shape for our parent function, because it's going to tell us how quickly the function is increasing. So this would be the 2 multiplied, so by it's 2 to a power, so it's going up every time 2 times as much. When you have a 3 as your base here, it's going up 3 times as much, and 4 is 4 times as much, and so on and so forth. But if we're going to look at this exponential function as a parent, we can then apply your shifting rules to the other functions. So let's take a look at that. Okay, let's say if we want to do negative 1/2. Okay, this would be right here. This is going to tell us, if we have a negative 1/2 here, that it's going to compress just like normal, and the negative will tell us that it's going to reflect. So we're expecting this thing to go around the x-axis and be headed this way, because if you can imagine it reflecting, but this 1/2 tells us that each one of these values is going to be cut into half, okay, before it reflects. So if you go piece by piece, this one gets cut in half and then comes over and reflects and gets put right here. Okay, this one gets cut in half and then reflects and comes over here. This one is a 4 and it gets cut in half to a 2 and then reflects down here. This one is an 8 and gets cut in half and then reflects down on this side. So what you have afterwards is a graph that's continuing to do those things, but it's actually not as abrupt because it was cut in half. Okay, but it's exponential, which means it's going to start getting as abrupt after a certain amount of time. And it does flip over, so it's headed the other direction. Now, we have other things to consider. That's just if you have one thing happening. Here we have a stretch, and here we have a right 4. I did pause there for a little bit just so you can think it through rather than just hear it super fast. So this is going to go right 4 and it's going to stretch by 3. Okay, so it's not flipping over, but we want to take each one of these values and we want to stretch them. In other words, multiply by 3. 1, 2, 3 times 1 is 3. And then that 4 moves it 4 to the right. 1, 2, 3, 4. This value right here is a 2. Multiply it by 3. 2 times 3 is 6. So that would take us up to here, but then we need to move it right 4. 1, 2, 3, 4. This point here is going to get to be like super high because we're going to multiply that by 3 and then move it over 4. So 3 times 4 is 12. So 4, 5, 6, 7, 8, 9, 10, 11, 12. But then over 4. 1, 2, 3, 4. Okay, that's great, but we need to also, curve it down a little bit further. So we can even take that half. That half multiplied by 3 is 3/2, which is 1.5, takes us up to here. And then over 4, 1, 2, 3, 4. And so the effect is that we still have a curve happening. It's still coming down like this. But the whole thing has been multiplied by 3 and then moved over 4. And you end up with your new exponential function that has been based off of the original parent, shifted, multiplied, and then stretched. Okay, so let's take a look at one more before we go on to something that is even a little bit more interesting. Okay, so here's your parent. Here's the initial thing. It's not stretched, it's not compressed, it's not reflected, but this -3 tells you that the whole thing is going to move down 3 units. So 1, 2, 3 units down. 1, 2, 3 units down. 1, 2, 3 units down. And on and on and on for this. Now the thing that you need to keep in mind, there is an asymptote hiding here where it's going to 0. The asymptote has also shifted down, okay? So you have to be very careful when you draw these that you don't go down past that value. Okay, the invisible line that doesn't get crossed, called an asymptote. It has been at 0, but when the whole thing shifts down, the asymptote also. So do be careful when you draw these that you don't go past that lower asymptote, because if you cross over it, you would lose some points for that. So watch out for those shifts. Watch out for here. Make sure you don't cross over. My arrowhead can cross over, but make sure that your drawn in line doesn't cross over into where you wouldn't have any values. Okay. We have a special number with a special function right here. And we're not going to look at the graph of this, but just understand that it is an exponential function. And that base, in other words, that asymptote, that is called the natural base that it's been discovered, e. And that lowercase e represents the number 2.71828. That's not the whole thing. It does go on and on forever. It is called the natural base. That number is used in a special formula, and for our purposes, we're going to just consider how it's used in this formula, p(e) to the rt power. Now what I do want to address is why this constant is called e. And well, this constant is called e because of Leonard Euler. If you remember, we talked about Leonard Euler earlier in the year. He's in the poster in the back of my classroom. And Leonard Euler, the mathematician who had discovered about this, if you remember, he was the one who was very, very big on education and was responsible for a whole lot of our mathematics. But this is Euler's number, so E for Euler, and we can remember him. It's Euler, if you remember, and he was the one who had written his letters to a German princess to help educate her at the request of her father, the king. So this number, though, it's not just any kind of random thing or anything that's like lost in obscurity. This is used in the banking system for continuous compounding. And what continuous compounding is when, this might be familiar to you, you've got this amount that you're going to get is interest, or you're going to get as your total amount after interest is added. But instead of having every single year the interest put on and then it adds interest and adds interest and adds interest, in continuous compounding, that's happening right along the way. It does yield a little bit more interest that way continuously rather than incrementally where it's happening once a year. Sometimes banks will do daily compounding, which is a little better than once a year compounding. But if they do continuous compounding, that's the best for you. Okay, well then how do we calculate this continuous compounding? Okay, so this is the amount that would be in the account at a certain time, t. T is your time. R is the interest rate, just like we had the interest rate before. E is Euler's number, which is that 2.72 approximately. And P is the principal, the amount that was invested in the first place. So we'll take a look at a couple of examples here, just like we did before. Notice this example should look very similar to you because we used this exact same example yesterday, but instead of continuous compounding, we had it compounded once a year. Okay, so 5% interest compounded continuously. There's your difference in wording and how much you have now. So we put that into the PERT formula, PERT formula, okay? And when we do that, I want to show you how to find that in the calculator. Principal times E, E not being a variable, E being 2.72 approximately, but there is a button on the calculator to handle that. If need be, if you are stuck for lack of finding a calculator or that download that I told you about doesn't work, you can find the download for that. If you look right on the website at the bottom of this week's instructions, you find you can get a TI 84 Plus courtesy of Texas Instruments if you follow the directions on that and then pick for either PC or your Apple, whichever it is that you have. All right, so we have this and 0.05 because that's your interest rate, time being 6 years. And when you put that in the calculator, let me show you this. Here's just e to the first power, so you can see here's your whole long e with even more digits. But let's put in 1,000, okay, times, and e is hidden. It's the second of the ln button. We're going to be dealing with ln. ln stands for natural log, and we will talk about that when we get into our sections on logarithms. But at the second of the logarithm, you notice you have an e to the x button. And so we need to do second, and this will take e to a power, and that will be 0.05 times 6. Or if you wanted to multiply that ahead of time, you could do that and get your 0.3. That might be a little bit easier. And when we do that, you get $1,349.86. $1,349.86. Make sure you are rounding to the correct decimal place for money. And then we have that. Now, when we compounded that annually, the amount was slightly less. It was $1,340.10. And you might be like, okay, wow, a whole difference of $9.76. Woohoo. However, as you begin to work your way to being older and older and older, and you're looking towards retirement, that amount can add up if your investment is significantly higher than $1,000. And it's going to take way more than $1,000 for you to retire. So keeping those things in mind, if you're compounding continuously over a longer period of time with significantly more money, then your difference becomes greater and greater and greater. So just so you know, there's two different things, two different formulas you're responsible for. The one that we talked about yesterday, which would give you annual interest, and then this PE to the RT power formula, which gives you the continuous interest. All right, so that's about it for today. Take some time, go ahead and work on that assignment and get it ready. The sooner you get stuff out of your road, the less work that you need to do, and that's good. And I hope you have a really wonderful and restful weekend. God bless you.